Hello, everyone. My name is Jeremy, and today I will be presenting my Workshop 3. My research was over combat models for RTS games. Now, what does this mean exactly? Well, games that use AI require access to a forward model, or a combat model as the research I'm covering calls them, of the game at hand. And sometimes these combat models aren't readily available. The research I'm presenting shows how these combat models can be learned from replay data in the game StarCraft. So to preface this, you do need some knowledge on StarCraft and how the game works, just to kind of understand the algorithm. So why do we care to solve this problem? To start, RTS games have been a big part in research for AI decision making, and specifically an AI developed by DeepMind called AlphaGo. And if any of you aren't familiar with the board game Go, don't worry, I'm not either. But what's impressive is that this AI, developed by DeepMind, beat the second best Go player in the world, Lee Sedol, 4-1. And a lot of research has been done on this AI since then. We also care to solve this problem, or at least improve on this problem, because StarCraft AI competitions are held, and these kind of competitions promote a safe space for learning and improving AI for both students and researchers alike. So, what is an example of AI in an RTS game? Uh, Besides AlphaGo, Total War Rome 2 uses a searching algorithm called the Monte Carlo tree search, which breaks down decisions into playouts and assigns them a probability of winning or losing with that playout based on a few factors: uh, previous moves, data collected for these playouts, and other things like that. One problem with this method is the amount of time it takes to make a play. And as you can probably guess just from looking at this image, the searching style isn't efficient because it grows exponentially. A lot of players reported when Total War Rome 2 first came out that the AI would take upwards of 5 minutes to make its move. And although the moves that AI were doing were human-like and smart, the amount of waiting left people irritated. So they were eventually forced to prune some of the search algorithm in order to optimize it. And here's the algorithm I'll be covering. It's called the decreasing algorithm, and it returns which team, either team A or team B, wins a combat or a fight. It starts by taking the input of both teams' units, a damage per frame matrix, and a target selection algorithm. This damage per frame matrix, or DPF as it's referred to in the algorithm and in the future of this presentation, is calculated by using replay data extracted from 600 games and takes into consideration the damage and attack speed of their weapon, maneuverability when attacking, special abilities, and the specific enemy that's being targeted. The target selection algorithm also uses the replay data extracted from the same 600 games and looks at which enemies were targeted the most and least and assigns them what's called a board account. This board account is essentially used as a priority list for what units should attack what. From the input into the function, each team gets sorted based on their board account. That's the sort A target selection, sort B target selection. Then we enter the first while loop, which can't and won't be exited until the combat has ended. From the first while loop, the estimated time to kill for each unit is calculated in the TB and TA, and the algorithm predicts which group of enemies in the fight will win. As you see on the right, here's my line-by-line breakdown of the time complexity for this. And as you can see, the most costly part of this is actually the calculating and sorting of the team's board account. The rest of this is pretty efficient. So why is this algorithm better than other algorithms used in StarCraft AI? Well, to start, the decreasing algorithm uses replay data to give units a score as opposed to being random, using a pre-coded list or using a destroy score like a lot of the other StarCraft AI do. The destroy score is calculated by the price of the unit, which is the mineral cost plus the gas cost. And as you see in the picture in the bottom left, the left column, the percent accuracy of predicting whether a fight would be won or not is actually very similar across the board between random, destroy score, and board account. But the research here decided to use the board account because it has the potential to do better the more replays you feed it. Another reason why this algorithm is better is because it makes decisions based on the effective damage per frame, or the DPF, and not the actual DPF that the unit does. The effective DPF is calculated by taking the minimum amount of damage you might deal during a fight instead of using the average. And as you can see in the picture in the top left, this shows the win and loss percentage of 3 similar AIs that are used in StarCraft AI competitions. These two things do make it better. The average evaluation and the win percentage are both higher. And average evaluation is the amount of times it correctly predicted a fight, either winning or losing. Like if it predicted the fight as a win or a loss, that's the average evaluation. The loss percentage is 0 for sustained and the decreasing algorithm because there was a game time limit that the researchers imposed of 20 minutes. So games that they may have won or lost were cut short due to this time limit. And the researchers stated that they did this because they wanted consistent results and that most games were usually decided by 15 to 18 minutes anyway. And yeah, that concludes my presentation. I hope everyone enjoyed and found this interesting. Here's the citation and link to the PDF if anybody's interested in reading about it. It's 13 pages, but it's a pretty easy read, honestly. And yeah, hope you guys enjoyed.